Okay, so another topic that might be good to take a quick look at before we kind of start chapter 1 of AP Pre-Calculus is solving inequalities. That should sound very familiar because you've done plenty of that in previous classes like Algebra 1 and Algebra 2 especially. But it'll be like, so we'll do a quick review of that, but there's probably the biggest objective of this quick video is actually showing you an example or two that you've probably never done before. So a new kind of example of solving an inequality, just with one variable, by the way. It's probably just going to be x in every example here. So again, like I said, first kind of review stuff I assume you've not just seen before, but seen plenty of times. And so this is an example from your textbook, section 0.3, which is like a prerequisite chapter in the book. It's a chapter before chapter 1, so it's like chapter 0, section 3, basically. So hopefully this looks easy enough to do if you had to do it. This is the kind of example where you would basically just, even though it's not an equal sign and it's not an equation, you're still just going to get x by itself. Eventually, like that's what you want to do eventually, is isolate x, the variable, all by itself on one side of the inequality. So in this particular example, you ready? Hopefully you're trying to think one step ahead of me. You would, well, that's the original question, I think. So first you would distribute to clear the parentheses. Again, this is all just this is review before the, review kind of thing. So the distributive property, and then what you're probably going to want to do next is get x only on one side. I tell a lie. I guess there was I agree with that. There was definitely some like terms on the one side, so combine that. Now we're probably ready to know. Okay, this is not wrong, but this is not usually what I would do. Normally I get the variable on one side first, then I would worry about, putting, that kind of stuff. Anyway, there we go. So then, or you could think of this as dividing both sides by -2, the inequality versus, yada, yada, yada. You just get x by itself. And keep in mind, this is an infinite number of solutions. There's an infinite number of numbers that are greater than or equal to -3.5. And as you probably remember, oftentimes you take this and you make a little graph on a number line, right? Where you put a, open circle or a closed circle on -3.5. What would it be? It'd be a closed circle. And then you would shade to the right of -3.5. And hopefully you've already seen the video, or we've talked about in class or whatever, about interval notation. So this is saying the same thing, from -3.5 all the way to positive infinity with the bracket, because -3.5 is included in that set. Anyway, let's try to keep this rolling. So just like another example from basic linear inequalities. This one involves fractions. I just want to highlight one step here. If you want to pause the video or slow things down and take a longer, closer look at this, that's fine, but I just wanted to emphasize one step, because I wonder if you've ever used the trick of clearing if there's fractions involved in an equation or an inequality or something, clearing all the fractions away by multiplying both sides by whatever is going to clear all the fractions. You can think of it as the LCD. So look at all these denominators. The LCD of the denominators is 12. So if we multiply everything by 12, the fractions go away, and it just kind of makes things more simple. But and then yada yada yada. This one included the graph, so there you go. Open circle, notice, because of it's just strictly greater than. And that means, like, if you wrote interval notation, there'd be a parenthesis with the -2. Anyway, trying to keep this moving because we want to get to the new stuff. More stuff you've probably done before. Remember, there's like things that are called compound inequalities. This one, it looks like there are two inequalities here, and they're kind of like smushed together into one. If you were to separate these into like the two separate inequalities, the word that would connect them is what? Is it and or? When you have this kind of thing and you want to literally break it up into the two separate ones, the word would be and. But again, we got bigger fish to fry here in this video, so just you can take a look at this at your own pace. Where we would solve for x in the middle. That's what they're doing here. They're not separating it. You could like literally write this into the two separate inequalities, but this is what I do also, what I like to do, just leave it and just kind of work on getting x by itself in the middle, which is here. And you got to remember that this means in between -7 and 5, which looks like we're including 5, but we're not including -7, hence the open circle here and the closed circle here, hence, which is, the parenthesis and the bracket. Different section of the textbook in chapter 0, but again, just trying to give a full background story of what you've probably seen before with inequalities. Remember how you could do absolute value inequalities, and so if you had something like this, as long as you had the absolute value part isolated, you could break it up. This is the original. But if the absolute value part is isolated, you can break it up into two separate inequalities. So what I usually do is write this into like two separate ones, which would be, it's the same as this, but what I would write down if I was doing this would be x minus 4 is less than 8, would be the one case. And then the other one would be x minus 4 is greater than -8. So I would write x minus 4 is less than 8, and, the word is and here, x minus 4 is greater than -8, which that's what this says. Okay? And then the bottom line is you solve for x. So again, what this basically says is that x is less than 12 and greater than -4 at the same time. Notice the strictly less than, so parentheses. I don't know if there's a... okay. So graphically, well, hold on. Let me not get too far ahead of myself. Okay, this is talking about the graph. Figure 2 shows that points on the... okay, well, I don't want to confuse anybody. Graphing-wise, if you were going to, like, graph this answer, it would just be a number line, okay? Let me say that again. Doing it algebraically, sorry, I hit the microphone. Doing this algebraically, you get this answer because of the whole 2-case stuff and turning it into a compound inequality. So the graph of the answer is on a number line, open circle on -4, open circle on 12, and the two graphs would head towards each other, and then sometimes I say they collide, but really it's these two graphs that you're really just taking the intersection of them, like you're only keeping the overlap. So when the graphs collide, you just kind of like stop, and you're just going to shade everything in between -4 and 12. What this is right here is kind of like another way to do the entire problem entirely. So it's like a graphical way to do the problem from the get-go, which you can kind of treat this as a function. So just this part is like y equals the absolute value of x minus 4. Remember, that's a v graph, and you're seeing, for what values is the blue v graph going to be less than or below this y equals 8 line. So it's like, so look at this. It's kind of like saying, when is this graph, if you made it into like a full function with y, for what values is that? less than or lower on the graph than this if you turn that into a function of like y equals 8. So take a look at that again. I don't know. I usually don't do it with like as a graphing method to come up with the answer. I guess I always just do the two cases and I do it analytically or algebraically. But hey, there's a graphical way too. So that's new. That might be the first like totally new thing as we review some old school stuff. Is like, oh my gosh, you could do inequalities like this graphically. This one is like the last kind of one that you've seen before, you should have seen before. It's just another absolute value inequality, which means you're going to be breaking it up into two cases, which turns it into a compound inequality. But this one, because of the symbol, is an OR. Like when you break it up, it's 3x minus 2 is... I do this one first. Man, some differences here in this textbook from what... But I do this one first. This is like the first case in my mind when I do it. So it's 3x minus 2 is greater than or equal to 5, or 3x minus 2 is less than or equal to negative 5. And then you just solve each one, solve, and then you end up with this, which is, if it's OR, normally the graphs are then going to be running away from each other, and you're keeping everything. So here's like the solution, and likewise you could have done it graphically from the beginning. Okay, but if you wanted to take this final answer and make like two graphs on a number line for the answer, that's what you've done probably 100 times. But this would be like instead of all of it, and then you would take this and you would interpret this graph and then maybe put that answer on a number line, because when is it greater? So when is the blue V higher than the red line of like y equals 5? So anyway, but that's old stuff. So I think we're finally, I don't know how many minutes into the video, but finally going to show you an example that you've probably never seen before. So I think we're going to do 3 or 4 quick ones. Maybe. So, okay. So notice that this is quadratic. Like this expression over here in this inequality is quadratic. If this was an equation, what you would remember like what you learned in Algebra 2, if this was just an equation with an equal sign, what would you do? You can't just like get x by itself. So you would do things like try to factor, after like setting equal to 0, you would try to factor. You might end up needing to do the quadratic formula. But here it's funny, you're going to basically do that anyway. Even though it's an inequality, here's the way you handle these. You first solve that corresponding equation, and like I just said, what you would probably want to try first is factoring, if you could. So do you remember how to, can this factor x squared minus x? Minus 12, how would this factor? I might end up making a factoring video too, so maybe, I haven't, as I record this, I haven't made it, but like maybe you've already watched like a factoring review I did, but so factoring here would be just unfoil. And if you solved it, you would get x equals 4 or x equals negative 3. So once you figure out when this is equal to 0, so ultimately we're trying to figure out when will this be greater than 0. So first you figure out for what values it's going to be literally equal to 0. And then I think what this textbook is doing is that then you look at the graph, which you could have looked at the graph from the get-go, like I've been kind of talking about. So I don't need to move it, do I? So the graph is the blue parabola here, right? And really, if you just wanted to do it graphically, you're just looking at it and going, okay, like for what values is the parabola greater than 0, which means above the x-axis. So if it's, look, if it's above the x-axis, that means like it's greater than 0. It's like it's essentially greater than y equals 0. Remember, y equals 0 is the x-axis. And then since you did it analytically over here, when you look at the graph, you can now with like absolute certainty say, oh, so that looks like -3, but it absolutely definitely is exactly -3. Oh, this on my graph, this looks like it's crossing at x equals 4, but when you look at the analytical work, you can, okay, it for sure is exactly x equals 4. And then you can just see how from -3 into the left, and then from +4 into the right, this graph, this x squared minus x minus 12, is going to be greater than 0. Here's what I would do, like just the way I was taught growing up, and this is something that people do in calculus a lot. Like when I say this is what I was taught growing up, I'm thinking of like when I took calculus and when I teach calculus. Instead of doing this graphical kind of approach, once you have these values, you can do something that is called number line analysis, which means like you just kind of jot down a quick little number line. And so -3 and +4, that's when it's equal to 0. So here's what we do. So this is basically breaking up the number line into like 3 pieces. We have like this piece over here, we have like this chunk in between, and then this chunk here. And basically all you do with this number line analysis is you pick a random number, like -5, any number you want to pick, like on this part of the number line, and you test it. So if you were to plug in -5 in for like this into the original inequality, -5 squared, that's +25, okay, minus 5, okay, that's like adding 5, so it'd be like 30. And then 30 minus 12 is what, 18? So like, does that make it true, right? Is that greater than 0? Yeah. So, and then you just kind of, maybe here you test, 0, right? And if you plugged in, so like a number between -3 and 4, I would definitely pick 0. So like 0 minus 0, or 0 squared minus 0 minus 12, you get -12, which is, it's not greater than 0. You know what I mean? And then if you picked a number here like 5, okay, you'd get the kind of the same thing. So turns out that these are the 2 sections of the number line that contains numbers that make that true. So again, I just picked -5. That means anything I would have picked, because -3 and +4, those were like the magic numbers to break up the number line. Okay. This next example is kind of the same. For this one, remember, when you're just trying to treat it as an equation to solve, you need it equal to 0. So I don't know if so what would you do to solve that? Remember, you would first try to factor, and if it doesn't factor, you would probably have to go with the quadratic formula, okay? Especially if you want to like look at a graph, if you were just going to do it graphically. Like you maybe want to have more evidence of like what these points are, but so what would you do? Can you factor this? The answer is yes. And what you might be thinking, or the way you might have, so this was just quick, like, okay, here's the bubbles, here's the unfoil. But what we usually do to get to here is we do this whole Phoenix method, So this is where like a teacher like myself would say, well, geez, if we want to try to unfoil this, because there's no GCF, so if we were going to try to factor this, we would go with like unfoil, but that would mean, maybe using the Phoenix method. Some people can unfoil it just in their head, but like what this person in this textbook did here. But this would be unfoil, and then, solve, solve, solve. And so we get these values, and that's what I would use to kind of break up the number line, test a number like -5, and then test a number like 0, and then test a number like, not 1, 5 over 2 is 2 now, so like test a number like 3, like I would test 3, and it turns out, like if we're looking for anything less than or equal to 0, less than or equal to 0, remember, like whether it's less than 0 or less than or equal to 0, that matters for like your final answer. So I think we're just looking for like these numbers are what's going to make 2x squared plus 3x minus 20 less than or equal to 0 or below the x-axis. Here you would just be looking to see, like, if I plugged in -5, would it make this true? If I plugged in 0, would it make it true? If I plugged in 3, would it make it true? So yeah, it is everything and including, in between and including -4. So really just this. So this is the interval of solutions. But with the brackets, because we are including -4 and 2.5 because of that. These last two examples, I don't even think I covered anything up, so you can just look at them at your own convenience. I think this one was basically where you could use the quadratic formula if you wanted to do this analytically. And then that way, when you're looking at the graph and you have to like zoom in or something, and you're looking at an answer like this, and it's weird, that's because you would have had to like do the quadratic formula and get some like square root irrational answer, But so this is probably showing the graphical sort of approach where you just look and you got that answer, and like when is it greater than or equal to 0? That means when is it above the x-axis, and so the answer would be right there with the union, like two different sets but together. That's just in case you've never heard me say in a video or in person, that what that symbol means. It's just like it's these two separate intervals but together in an answer, so the union of those two intervals. And then this very last example is just one of these wild card things where turns out that there is no values of x that make this true, and then the graph shows it. Like if the parabola is never less than 0 or below the x-axis, then it's no solution. But alright, that'll do it for that video.